Swayam Prabha. Digital India. Educated India.
Hello and welcome back. So in this video we are going to look at the non-rigid matching or registration algorithm called the Demons registration by the author. The author's name is Tyrion. This is a very popular algorithm. It's been around for some time and people still use it for non-rigid registration, primarily because of ease of implementation, and also it's fairly quick algorithm, especially if you're trying to do 3D non-rigid registration of medical images. So we will actually look at how the deformations are computed first, and then we go back to why this is called the Demons registration algorithm. Okay, so in this paper, in the section 4.4, this is actually a report. We are going to look at something called the optical flow, based on which the deformations or individual pixel deformation fields are computed. Okay, so if you consider an image I, okay, and you say there are objects in the image at different locations x, y, z, and you also treat this as a function of time. In optical flow, basically you are trying to look at moving frames. That is, in a video you're trying to track objects in a video, etc. This optical flow is very useful. So the assumption is that the brightness of the object doesn't change between frames. When I say brightness of the object, I mean the pixel values comprising the object, or the values of the pixels comprising the object does not change between frames. So if that is true, then I is a constant, right? This is a constant for a particular image, and we can say that di by dt equal to 0. So this is what is meant by this condition here. One second, right there. Conservation of intensity of points under motion. Okay, so if we are looking at a video frame as an object is moving in the video frame, and then the pixels which comprise the object, they don't change too much in intensity, and of course the assumption is also that the motion between two successive frames are not large. So in our case, there are only two frames, basically the moving image and the fixed image, right? That's what we are going to look at, and we will see how we can use this paradigm to arrive at a expression for the displacement field. Okay, now this di by dt equal to 0, because I is a function of x, y, z and d, we can use chain rule to arrive at the following expression, so which is given here. Let me use this. Given this is expression, right? So this di by dt equal to 0 it translates to using the chain rule in this form. Okay. So what is this delta I over delta t? Delta I over delta t is if you discretize it, then we are just basically comparing the image intensity across two different frames, or in this case image intensity difference between f and g, where f is the fixed image and g is the moving image. So then we can write delta I over delta t is equal to f minus g, and then of course when there is a minus sign we get equal to g minus f. Okay, the left hand side of this equation, it can be written as v dot delta f. We can see that very easily. Let me just, if you're not sure, let me just write it down so that you understand where this comes from. So this left hand side can be written as delta I by delta x, delta I delta y, and delta I delta z, and then you have your delta x, delta t, delta y, delta t, and delta z by delta t. Okay, so this is basically think of it as a dot product. That's what is written. So this is your V vector and this is your delta I by delta X, delta I by delta Y is a three-dimensional gradient vector. So this is gradient of F. In this case, no, I'm using I, but then, in the context that we are looking at F and G, where F is, one frame and G is the other frame, this is just nothing but with respect to the fixed image frame gradient of F. Okay. So that's why we get this V dot gradient of F. Okay, and it is equal to G minus F. It's actually G minus F by some delta T, and we set that equal to 1, so that that's not explicitly shown here, because in order for the units to match on both sides, here V is a velocity. Okay, so the one way to understand this equation is that if you have, let's say if you consider like a one-dimensional, a row of pixels, that's your image, and if you have a slight motion of that row of pixels, and if you're looking at the difference between after the motion, if you're going to look at the difference between the pixel intensities, before and after motion, then you can say that, that this difference in intensity is equal to the speed at which the frame moved multiplied by the rate at which the pixel values are changing. So for a very small enough deformation, that's true. Okay, so then we can write it in this form. That's the explanation for this equation. Okay. So this is your optical flow equation, and this has a problem because this is underdetermined, right? Because if you see, V has 3 components, okay, and in many cases, let's say if you are looking at 2D images, V has 2 components, but you have only one equation, right? Because we are actually trying to estimate V, because in this case we are looking at fixed frame and moving frame, and we are assuming that delta T is equal to 1. So V is basically dx by dt. That's what we see here. And we can just, we can always replace V with the displacement vector rather than use V. So this V is what we are trying to estimate. And so the equations is not, number of equations is not enough. So what in this paper, what the author did was, he chose a regularization, if you can call it, or a constraint, I should say, on V. He just said that, the author said that V is, let me just add this. So V is proportional to the gradient of F. Okay. So the way I understand it, at least, is that, or some V equal to some alpha times gradient of F. Okay. Now if you assume this, then you can plug this back in the equation we saw, wherein V dot gradient of F equal to G minus F. If you substitute this, then you get the value of alpha, right, to be, substitute for, instead of V, substitute alpha gradient of F. So alpha will be equal to G minus F divided by gradient of F squared. Okay, and then you put this, now that you know alpha, you can always get V to be G minus F gradient of F divided by modulus. Okay, so this is what we got. Okay, now there are some problems with this equation, because it can be, it can blow up, because when delta gradient of F is very small, you can get very large errors. So there is some form of a normalization, or in this case, some you can call regularization of this expression, wherein instead of just using this, you have an additional term. So you rewrite it as, let me rewrite it as, G minus F gradient of F squared plus. So if gradient of F, sometimes it's small, it's offset by this number, which in this case it's very small. You still have this to regularize the denominator so that it doesn't become too small and blow up. Okay, so this is the update. So this is V, right? So if you have, so you can, for each component of V, you can get this expression. You have a displacement field. Of course, in the context of registration, V is basically proportional to your displacement small d, because we are looking at, let's say, unit time interval, we assume, and then so instead of calling this velocity, we call this the displacement field. Okay, so this is estimated. Okay, on top of this, there is also a constraint to be, not its constraint, regularization to be done. So why do you need this regularization? So if you think of a grid, right, and if you're looking at the displacement vector, right, displacement vectors, right, if you think of it, there is no, I mean, the displacement vector can be in any direction, right? You're not constraining it at all. So this becomes this. So this is a very hard problem to solve, right? There's so many ways that you can displace your image, and try to match it with the fixed image. So there has to be some form of regularization. So in the original optical flow equation that we saw earlier, people used, it's called Horn-Schunck flow. People use some form of variational techniques to impose that regularization by, imposing smoothness constraints on the on the velocity field. But in this case, they did a very simple regularization by doing a Gaussian smoothing. So what does Gaussian smoothing do? All you do is you replace. If you based on this formula, you get an estimate for all the pixels in this grid. So you replace, for very crudely speaking, you replace the center value with the weighted average of the neighborhood. Okay. So since this is a vector, so you kind of can average by component. Okay. So you replace every component with the average of the corresponding component in the neighborhood using a Gaussian weighting rather than uniform weighting. You use a Gaussian weighting. Right. We saw that that's a Gaussian filter. So that's how it works. So the width of the filter sigma is a hyperparameter that would control to how much, you can call this a rigidity constraint, right? So, you're kind of smoothing it so that, it's kind of uniform in a certain, it doesn't change very rapidly in a certain neighborhood. You get the same kind of displacements, and or smaller displacements. So also note that we are using we are trying to approximate V with using the direction of gradient of f and the magnitude of the gradient of f. You might ask why would we want to do that? So one way of understanding is that we want to move in the direction where there is more heterogeneity, right, where there is greatest change in the image. So in the fixed image, gradient of f tells you the direction of greatest changes. Okay, heterogeneous regions. That's where we want. Then we want to move in those directions, because wherever gradient f is very small, it means it's a very flat region, and you really don't have any information there. Okay, so that's one thing that helps if you move in the direction of gradient of f. Another thing is, if you look at images. So, for instance, if you look at boundaries of organs. So let's go to another slide. So let's say we have a kidney. Let's say something like this. Okay. If you look at its boundary, or boundary of any organ for that matter, right? So this you can interpret as a isocontour. Isocontour or regions or lines of similar intensity or same intensity. Okay. So if you take a gradient, the gradient is always perpendicular to the direction of the isocontours. If you take an image, so gradient of f, if this is the image, then gradient of f is always perpendicular to the isocontours, right? And this is good because it's very hard, in fact near impossible to to figure out motions along regions, along lines where the intensity does not change, right? So let's say you are perfectly, just to give an example why that is the case, where you can't determine anything along regions where there is no change is in intensity, or gradient of f is 0. Basically, that's true. Gradient of f would be 0 along the contour, along the edges, right? So if you have any kind of displacement along the edges, anyway, it's going to be impossible to figure out, right? So you can think of an example like if you have a disc, okay, and it's of uniform color here. Let's say this is all blue. It's going to write no. If it's spinning, let's say it's rotating, you wouldn't know. Right, if it's a very solid same color, only if there are variations in the intensity on the face of this disc, only then can you see it spinning. Otherwise, it's impossible for you to see it spin. So similarly, it's the same case. If you have no variations along the isocontours, basically along the edges, you might not know, or wherever the gradient of f is 0, you cannot estimate any displacement. So then you only look in directions which are perpendicular to isocontours or along the direction of the gradient. That makes more sense. So that's why you put your V is proportional to gradient of f. This is one explanation you can think of. Okay. The author in this paper gives some geometric explanations, but I have given you this. You can also read the paper to understand the geometric explanation. Okay. So this is the overall idea. So there is a first step is you estimate the displacement field, and then you regularize it by smoothing with the Gaussian filter. Okay. The regularization is an essential step. Otherwise, because the problem is ill-posed, right? You have so many directions in which you can move, and unless you constrain it, you cannot solve it. It will blow up very quickly, your solutions. So, and in the paper, the author suggests multiple variants of the formula that we saw to estimate the displacements. So it's all given there. So please go look at that. But this is the one I showed you was the standard one. Okay. So that is usually done. So that is just to rewrite it. You would estimate this as G minus F gradient of F divided by gradient of F squared plus G minus F. So this is proportional, something that you would do for the displacement field. So this is a very simple and efficient technique. This followed by Gaussian smoothing. That's the two steps for the algorithm. So here this is an iterative algorithm. So what you would do is you would first start with an identity transformation wherein you don't do anything. You start with the fixed and the moving image. Use this formula to estimate, let's say, T1 transformation 1. This transformation is nothing but a bunch of displacement fields for your image. Here you would consider all the pixels in the image. So it means that you would estimate a D for every pixel. So D for every pixel in the image, where P refers to the position of every pixel. So remember, we always do registration in physical coordinates. So P represents the physical coordinates of the pixels. In the moving image, so you estimate for every pixel in the moving image a corresponding D of P, right? And well, you can do either way, right? So there is an inverse transform also. So it's up to you. So you have a displacement field that you figure out for every pixel, correct? And you smooth it with the Gaussian. And after smoothing, then you apply it to the moving image and then come back to this step. Okay, so it's like, and once you do that every time you have to update the transformation also. So initially you have identity transformation. Now you have to update the identity transformation with this. So then you have a new transformation. After this, once again you deform the image and then perform this step, whatever you're seeing here, followed by Gaussian smoothing, and then you go ahead and update the deformation field or the transformation. So you keep doing that till a fixed number of iterations, and then you stop. Okay. So this is the typical algorithm for the Demons registration. Okay. Very simple technique. Computationally, and so very popular, and a lot of analysis has been done. Now this is equivalent to minimizing a certain type of loss function. If you want to do gradient descent on a loss function in order to estimate the D, there are papers which talk about how we can interpret it that way. But from the point of view of optical flow technique, this is the easiest interpretation. Okay, so the author calls it demons. Okay, we will see why he calls it demons shortly.